All right, how's it going? So we're back, which is good.
I've completely forgotten how to code.
Yeah, I know. Like, what is C? I was really thinking we were going to be out there like 2 weeks. When it didn't end after a day, I was like, it's going to be long. So, kind of a change of gears to come back in. But I'm glad this ended quickly, so thank you for your patience through all of this. We've lost 3 days of classroom time, which is not a huge deal. Okay. We're probably not going to get any snow to speak of this quarter, but we've had times when we've missed that much through snow and so on. So that's not going to affect us as far as how much we cover and stuff like that. I've made a few tweaks to due dates on Canvas, most notably programming assignment 1, which was supposed to be due tomorrow. I've moved it back to a week from tomorrow. So it's due on the 24th instead of the 17th. But don't wait until the 24th to do it, or the 23rd. I would like everybody to finish PA1 by Tuesday. Okay, now I'm not going to grade it, I'm not going to require it to be turned in until a week from tomorrow. But I want you to try to finish it by Tuesday. Okay, so that's 3 extra days. Beyond Friday, we lost 3 days. So time-wise, right? Plus, you know, that's the weekend and Monday is a holiday. So it's 3 days, and I know you have other stuff to do, but it's 3 days without school in session to work on this. I would like you to try and think of it in your mind as this should be done by Tuesday, okay? Tuesday, we're going to start talking about PA2. And PA2 will be due 2 weeks from tomorrow, so it's due on the 31st. So if you think of PA1 as actually due a week from tomorrow and you don't start it until next Thursday and you finish it up Friday morning, then you've only got 1 week for PA2. PA2 is doable in a week, okay? But we're going to be talking about it starting on Tuesday. We're going to be talking about it all next week. You're going to be writing ODPs related to PA2, so you want to be able to kind of shift gears into the PA2 mindset next week. Okay? If you really need the extra time to finish PA1, you've got until the 24th. But we're going to switch into PA2. PA2 is basically PA1, but done the actual data structures way. So we're going to use mallocs to create nodes. We're going to be creating these nodes on the fly at runtime, storing them in memory locations that malloc gives us, releasing them using the free function, and sort of building this list out of thin air or thin memory. And conceptually, it's a big change. Okay, it's probably the first time we're going to be creating these structures in memory while the program is running instead of having them kind of pre-exist at compile time. It's a big change conceptually, but once you've conceptualized it, the actual writing of PA2 is really fast because it's going to be almost exactly PA1. We're just going to change how we interact with these nodes. And if you followed PA1, if you're using get node to find a new node, you're just going to replace that with malloc. If you're calling release node to reset the valid flag, you're just going to call free. And instead of using list bracket index, we're going to use pointer to list arrow in the index. So it's nowhere near as much work writing PA2 as PA1 once you understand conceptually what's going on with dynamic memory. So it's going to be a lot of working with that next week. And then PA3, 4, 5 will be, well, I haven't announced the dates yet, but they'll just continue 2 weeks apart. I'll start posting ODPs on Tuesday, so nothing today or tomorrow or over the weekend. So I'll start posting on Tuesday, and these will be ODPs related to PA2. Quiz dates are still the same, and once we start talking about PA2, we'll run through the GDB quiz and maybe do some of that as a class exercise. Okay, that's going to be a really good practice in using GDB to examine memory, and I have a file sitting under /temp that you can play with. Well, we'll talk about that in detail and what's involved in that. If you want to get a leg up on it, feel free to take a look at the quiz on your own before then. So we'll pop into the quizzes next week also. And I think those are the only dates that I changed. Everything else should be basically the same. All right, so any questions, concerns about logistics? So I posted an announcement. I have a PA1 sample main sitting on the server under /temp. If you're finishing up PA1, you're not sure exactly what it's supposed to do from the description, you can run this, and this is a version of PA1 that would get full points in terms of its behavior. So if I say insert 10, it says success, right? And if I say print, it shows me my list has a 10 in it. And if I insert 5, it says success, and the print shows me that. And if I insert 20, it says success, and the print shows me that. And if I delete 5, it deletes that. And if I try to delete 5 again, it says node not found. And if I insert a 15, my list looks like that. So you can use this to kind of, final check your code and make sure it's doing the right thing. Okay, so I added an extra feature in here, and this is not something you want to implement yourself for the final version, but I added this extra command called v for view, right? And v just prints out the contents of the first 15 entries in my struct node array. So I can look at this and see, okay, with that combination of inserts and deletes, here's what my struct node array ended up looking like. My sentinel node points to 1, that points to 2, that points to 3, and 3 points to my null. And unless you initialize your data and next values, these fields will be effectively random until you actually use the entry in the array. The valid flag should be meaningful everywhere. So if you're starting from scratch, right, there's my initialized array. That's what my init function does from the old ODP. It sets next to -1, valid to 1, and data to whatever. And set all the other valid flags to 0. And if I insert a number, that number went at index 1, and my sentinel node at index 0 points to 1 because that's where my first node is. And if I insert something before that, so now I have a 30 and a 50, this is what your array should look like, at least the first 3 entries. So the first entry is a sentinel that better point to node 2. Okay, even though the first node is a 30, 30 should be stored in index 2, and the sentinel should point to index 2. And then that node should point to index 1 because that's where the 50 is. And that node should point to my null. And if I look at your array and index 1 has a 30 and index 2 has a 50, something is wrong, right? You print it out, it's going to look fine, but it means you're doing something different from what the assignment specifies, right? So if you write your own view command, this is what your array should look like. And if it doesn't, chances are your main program is tinkering with this array in some way that's outside what a linked list is. For example, it's going through the array and it's looking at each number and finding the first number that's bigger and moving it somewhere or something like that. So make sure you're treating this as a linked list, right? Not as an array of struct nodes. It is an array of struct nodes, but more importantly, it's a linked list. Right? The only way you're allowed to move from node to node is by following the next pointer, starting with the sentinel node. So that's available if you want to do some checking on your code. And if you have any questions about why this is doing something, right, that's really good stuff to ask. And I did not compile it with the -G switch, so you can't see the source code. All right, so let's pseudocode our add function. So I made some clarifications on this assignment. So one of them being the add function just returns a 1 or a 0. It returns a 1 if it succeeds in adding the node, 0 if it does not. The reasons it might not succeed in adding the node is either there's no space left in the array or the number is already in the list. Okay, so your add function should make sure the number is not already in the list. If it is, return a 0. Okay, if the number's not in there and you have space to create a new number in your array, you have an entry that's valid, is equal to 0, then add should end up returning a 1. Delete, you pass it the number that you want to delete from the list, right? The data value of the node you want to delete. But this release node function, you pass it an index number. Okay, release node, you don't pass it the data value you want to, of the node you want to release. You pass it an index number. So, I shouldn't have cleared out that window. So if this is what my list looks like, right, Sentinel node is pointing to a 10, and the 10 is pointing to a 20, and the 20 is pointing to a 30, and that's the end of the list. So my delete function, I would say something like delete 20. Which would say go ahead and remove the 20 from the list. So I'm going to start at the first node and I'm going to search for a value whose data is equal to 20, and I'm going to adjust pointers accordingly. The release node, once I've decided that this is the node I'm trying to get rid of, release node, I would pass it the index of the node I'm trying to delete. Right? If I say release node 20, then my release node has to do what my delete function does. It has to look through the list and all that kind of stuff. Release node is a lower level routine. Just tell it which index. And it's really a one-line function. List bracket index number dot valid equals 0. That's all it does. Does that make sense? That's really all it's doing. And yeah, you could do it in main, but I'm not letting you do it in main. I want you to do it in a separate function. All right, one other thing, make absolutely sure that none of these functions ever print anything except for the print function, which is supposed to print stuff. But none of these things should ever print out error messages. They should not print out success messages. They should not print out helpful information about what's going on, except when you're debugging your program, right? But the version that you turn in, these things should all act silently. If you try to add something and there's no space left, just return a 0. If there's an error message that needs to be printed, the person who's calling the add function should notice that add returned a 0 and say, we did not succeed in adding that value. Right? Although your main program should just say success or out of space or number already in list. All right, same thing, search, don't print out node has been found, node hasn't been found, just return a 0 or a 1. The reason being that basically, even though we're writing these functions and we're writing the main program, we're kind of moving into a mindset where we're developing a package. of functions that, you know, maybe we're going to put on GitLab and advertise to the world, and other people are going to download and use, right? So we're making a package of linked list functions that other people can use however they choose. And here's, you know, documentation that tells you what these functions do. And so, yeah.
So you're saying whatever the return value is on the function, pass it to main, let main print out, whatever.
Yes, yes, exactly. So yeah, think of a package that would be generally useful. So the example I gave in the last class was, you know, scanf takes a string and, you know, a %d, and it looks to see if there's an integer in the beginning of the string. And if there is, it converts it, it stores it in an integer, and scanf returns a 1, saying I converted one thing. If the string does not begin with an integer, scanf will return a 0. Okay. Imagine if scanf also printed an error message. If you tried to convert an integer and it didn't find an integer, in addition to returning a 0, suppose it printed out, you know, warning, warning, extreme danger, I did not find an integer in the beginning of your string, please check your string and try again. Okay? That would not be a useful function. Because what do we do with scanf? We use it to parse things. We want to know, does this begin with an integer, does it begin with a character, does it begin with a float? So we call scanf a bunch of times on the same string with different formats. And we're looking at the return value to tell us what it's finding out about the string. If every time we do that, it prints out this big long error message, right, our code is going to look really junky. So we leave these things to be basically small building blocks, and we can add other functionality to what these things do by whoever's calling these things. Okay, but these try to do sort of the minimum amount possible, which is try to add and tell me if you succeeded or not. Try to delete and tell me if you succeeded or not. And this is going to be kind of our mindset throughout this course. We're going to be developing packages of functions, libraries of functions for different types of data structures. And we want to sort of keep in mind trying to keep these as general purpose as possible, even though we're the ones using them. Keep them sort of like small functionality, right? Just the essential behavior, and then that can be added to by the caller. All right, let's talk about the add function. Let's write some pseudocode for this and talk about how we actually implement add. So add takes a struct node array and an integer. And I want to think very high level. Let's forget about C, even though I just wrote C code. Let's forget about C for a few minutes. And just think in terms of high level behavior of this function. What kinds of things do we need add to do in order to accomplish this goal of inserting a number into a list?
Check if the number already exists.
Check if the number already exists. That's probably our first thing to do. Because if the number's already in our list, we don't have to do anything. Just return a 0, and we're done. So, so first step, if num is already in the list, return a 0. Alright, so that's our first order of business. See if the number is in the list. If it is, we're going to say we did not succeed in adding it, return a 0. Okay, suppose the number is not in the list. So this is a good number to try and add. What's the next thing we're going to do? Or some of the next things? Yeah?
Let me just see if we already found an open spot.
Doesn't look like it.
Already called get node.
Doesn't look like we've done that yet. Should we do that next? All right, let's call get node. So let's find a place to store this new node in our array. I'm going to take this higher level, and I'm just going to say make a new node. I'm going to call it new with data value equal to num. And that may or may not succeed. We can only make 99 new nodes, and then our entire array is going to be filled. So we want to make sure this succeeds. If there's no space, just return a 0, which says we did not succeed in adding. All right, number's a good number to add to the list. We've created a new node with a data value equal to num. What do we do next?
What's the next close number?
All right, so why do we want to do that?
Because we want to be taking whatever the next value is. And then
Okay, so let me go a little higher level for a moment. Find where the new node should be inserted. And then we'll add that detail in a moment. But basically, we got to figure out where in our linked list should this new node be inserted. And once we found that spot, then we want to adjust a few next values to insert the new node into the list. So that's a really high level view of our add function, right? See if it's already in the list. If it is, fail out. If it's not in the list, try to make a new node with the data value equal to the number we're inserting. If we can't do that, fail out. Otherwise, we've got a new node with our new data value in it, figure out where it should be inserted, and then tweak some of the .next fields so that that becomes part of this chain of nodes. Right, so it gets inserted into the list. All right, does this make sense so far? Okay. Oh, I forgot an announcement. So tomorrow, I'm going to do something special. I'm going to treat tomorrow as basically an open lab. So I will be here from 10 o'clock to 11:50 tomorrow, and this is a time to come in and work on code with me, or by yourself if you prefer. I'm not going to lecture. Okay. If you're done with PA1, take the day off if you want, or take the morning off, or come in and work on PA2 or something. If you're almost done with PA1 and you're pretty sure you figured out how to make it work and you still have to type it in and fix syntax errors, right, and you don't think you need to come in and work with me, that's fine. Okay. If you're not done with PA1 and you're not sure exactly how to finish it, or if you're stuck at some point and you're not sure how to get beyond it, or if you've got code written and it's seg faulting, or it looks like it's working but your nodes are disappearing, or you're getting random numbers sometimes when you try to delete the first node, come in tomorrow. okay? And we can look at what you're doing, we can go through GDB together, we can look at code, things like that. If you haven't started writing PA1, if you don't have any code written down, see if you can write some code between now and tomorrow. And if you can, bring that code in and we'll see where you are and we'll talk about how to build from that. If you have not started writing any code and you don't have any code written by tomorrow morning, come in anyway, okay? At the least, you've probably made a stab at the ODPs, which are part of PA1, right? So we can look at the code that you tried for the ODPs and we can talk about how to add to those to make them part of you know, some of these functions. And then we can talk about sort of where to build from that. And I would like, you know, by the end of this tomorrow that everybody at least has some code for PA1 that they can compile and they can run a test main program on and see that it's doing something. If it's initializing your list and you can see that it's initializing, that's great, right? If it's looking for an open spot and it can tell you where the open spot is, that's great. If it's the start of an add function that adds at the beginning of a list, right, that's great. Wherever you're at, come in, bring a laptop if you have. If you don't have a laptop, I might be able to borrow some if you warn me ahead of time, or we can work on my laptop. And it's really just I want to be here for a couple of hours to let people, you know, sort of bounce things off me and see where you are and so on. If you want to come at 10 o'clock, you can do that. If you want to come for the whole 2 hours, you can do that if it works for your schedule. Okay, it's just going to kind of be open. It may or may not become a regular thing, I'm not sure. But I definitely want to do this tomorrow. All right, cool. All right, if the number is already in the list, return 0. How the heck are we going to figure out if the number is already in the list?
Compare the value that the user inputted with any potential value inside the list.
Okay, so start from the Sentinel node and follow it to the next node and compare each of those. That would work. What if we want to be even lazier? That's not lazy. What if we want to be lazy?
Would you try making a search function and using the search function?
Yeah, you're going to make a search function because that's one of the requirements, right? Call your search function. So do exactly what you described inside search, but inside the add function, let's just call search. Let's just say if search equals 1, meaning that it's found, then return 0. So we don't have to write a lot of code for add to do that. Just call your search. This is a little counterintuitive, right? If search is 1, then we want to return 0. If search is 0, then we want to continue because it means the number is not in the list, so we're going to go ahead and add it. All right, make a new node called new with a data value equal to num. How do we do that? Be lazy. How do we make a new node? Call your getNode function. Hey. Right? This is what getNode does. Right? What we want to do is we want to go through the linked list array. We want to find an entry where valid is equal to 0. It's exactly what getNode does. So, you know, new equals getNode list. It's another single line of C. So comment here, new is the index of the new node. This is going to be confusing in PA2 when we're working with dynamic memory. We're going to have these things like node or previous or current, and we're going to be wondering what exactly is this thing. We're going to picture it maybe as a rectangle with a line with a data value and an arrow on the bottom, right? But what is it actually? In the case of dynamic memory, it's going to be an address. It's going to be a memory address where this struct node is stored, right? But in PA1, it's a simple index. It's an integer. It's a location in that array of struct nodes. But we're going to need to keep that in mind because it's going to try to confuse us as we're writing code and debugging our code. So when I say the node, chances are I'm talking about the index value. Right? But sometimes when I talk about the value of a node, I'm talking about the data value of that node, which would be list bracket the index dot data, which is very different from just the index. So we're going to be challenged to sort of keep clear exactly what is what. This is where good commenting is going to come in. But if you get confused on this, right, you can do print statements. And if you print the value of a variable and it's a 5, and the data value is supposed to be, 17,000, well, take a look at your array. I'll bet you that at index 5 in your array, you have an entry with a data value of 17,000, right? So you can use that V option if you want to put that into your main program, or just, write something called dump array that prints out the first 10 elements in your struct node array and shows you all the values. Use that to help you. Okay, how do we know if there was no space left?
If get node returns 0.
Maybe. What were you going to say? Same thing?
I mean, get node has to search for a node that's actually, what's the word? Make valid. So if they're all valid already, then you can't really add anything.
Right, so how are we going to know that that's the case?
In get node, you do the checking for that.
Okay. And how do we get that information from get node?
You get to the end of the, or wait, you get node turns the.
So get node's supposed to return the index. You almost nailed it.
We have a variable with the return value of get node. And if the value of the variable is 0, we also return 0.
Okay, exactly the right idea. One small detail, it's not 0, it's actually -all, which is actually -1. But yeah, exactly that, right? So look at the return value from -all, from a get node, and get node will return a magic value if it's out of space. But the magic value is actually -1. And the value I wanted to use is -all. So that's just a flag. So yeah, so if no space, return 0. Well, this is just if new equals -all. Then return 0. So far, not a lot of coding to write for add. It's a couple of calls to other functions and some ifs. Okay, find where the new node should be inserted. So now we're back to where we were a little while ago. How do we figure out where the next node should be inserted?
Each new variable that goes through the linked list.
Okay.
If list bracket previous bracket
Go high level for a moment. Forget about the actual array.
If it finds a node with a data value greater than
what we're inserting, right?
yeah.
Okay.
Which,
So-
point to that. It would also be pointed to from the node that would previously point to the greater node.
Okay, so we want to find, so suppose our list looks like this. Here's a 10, and a 20, and a 30, and a 40, and a 50. And we want to insert 25. So we know, as smart humans, that we want to put it right here. Right in between the 20 and the 30. So I think you're saying find the node that's bigger than 25?
By having nested brackets on the list thing. So linked list, start bracket, linked list, start bracket, new variable index for the previous node, end bracket dot next, end bracket dot data. If that is greater than the new number,
Okay. All right.
we work with altering the dot next of the previous index.
Right. Okay, that's absolutely perfect. Let me break that down into some pieces, and then we'll end up right where you just said. So we want to insert before the first node that's bigger than num. So we could also say, let's find the first node where the following node is bigger than num, and insert right after that, right? Or find the first node that's bigger and insert before that. So find first node where the next node's data is bigger than num. That's the thing we're inserting. And insert after that first node. So here's a 10, the next node is 20, that's not bigger than our number. Here's a 20, the next node is 30, that is bigger than our number, so we want to insert right after that 20. So if we think of this first node as, let's just call it before. So this would be before. And again, I'm thinking of before as the index of that first node. Then what we really want to do, so here's our new node. There's our new node with a 25. We want to change before to point to our new node, and we want our new node to point to where before was pointing, so that our pointers change accordingly. So new.next, new should point where this before node is pointing. And I'm going to actually make that change on my picture. I'm going to look at where before is pointing, that's right here, and I'm going to change new to point there. And then I want before to point to my new node. So I'm going to say before dot next equals new. And that's going to change this to point here. So here again, I have my node with a 20 in it. I wrote the word before above it, right? And I wrote the word new next to 25. I'm thinking of these as indexes in my struct node array. Right, so if this is stored at index 3, then before is equal to 3. So when I say before dot next, I really mean list bracket before dot next. When I say new dot next, I mean list bracket new dot next. So the adjustment's not too bad, right? Once you have these variables set up that are pointing to the previous node, the node before the insert spot, and the node you want to insert, tweaking those next fields is one statement each. The trickiest part is this step 3, finding that before node. Okay, so finding the node right before the first node that's bigger than your number. So let's break that down. Thank you. So yeah, there's well, let me do that when we get a little more code. But yes, I will say it was from seg faulting. So find the first node. We're going to call the index before, where the next node has a data value bigger than num. And again, we're imagining inserting a 25 in this list, 10, 20, 30, 40. Okay, find the first node where the next node's data is bigger than num. So I may start with, let's say before is this node, right? The next node is this 20, its data value is 20, which is not bigger than the number we're inserting. So what do I want to do? I'm going to name this next node next. Or let me call it after. Okay, so if I have a node before, I can say after equals list bracket before dot next. So that's the index of the following node. The data value of that node is list bracket after dot data. So if list bracket after dot data is bigger than num, then what do we want to do? Insert new in between before and after. So that's that step 4 that we wrote a moment ago. So have your new point where list bracket before dot next is, and have list bracket before dot next equal to new, and then return.
The second condition for that, because then that would trigger like right away with that statement. So if you had a number, like just annual number, right?
Mm-hmm.
That's like a 2. Like you're checking, say, let's see. Oh, no, maybe actually no, that works, I think.
Yeah, if I'm inserting like 100, that's not going to trigger on any of these. But if I'm inserting something smaller in this first node, it'll trigger right away. Right. All right. So if this is not the node we're looking for, right, if the number after it is not bigger than our data, then we just want to move down the list, right? So it's really just before equals after. So move this to be before and go back and try again. So this will move after to be down here, And then we'll check list bracket after dot data. That's a 30. That is bigger than num, so we're going to insert our new node between, before, and after, right between the 20 and the 30. That's perfect. All right, but there's a seg fault that can happen here. Right, so this is the edge case that you mentioned. Suppose we're inserting 50. So we're going to get down to where this is before and this is after. And list bracket after dot data is only 40. It's not bigger than num, so we're not going to do this insert. We're going to move before to be this node. Up here we're going to say after equals list bracket before dot next. Well, what is the next field of this node equal to?
-1.
That's -1. So after is now equal to -1. And as soon as I say if list bracket after dot data, there's a good chance I'll seg fault because I'm using a negative index.
Which is why you would need an outer check to see if the dot next is equal to -.
So up here, if after is equal to -null, we're at the end of the list. We want to insert after the last node. So insert right after the before node, and then return. And so how do we insert after the before? Well, I'll just have before's next point to my new node and have my new node's next point to my null. So that's your edge case that keeps you from falling off the end of the list. And if you don't have that, you will seg fault every time you insert at the end of the list, including the first time you try to insert into an empty list. So throw this in a while loop, right? You'll kick out of the while loop when you insert either at the end or in between two nodes. And otherwise, you just keep moving down the list. Yeah?
Is there a reason to write it like insert after the before rather than prior to after?
You can do it either way. The only trick is if you want to insert prior to after, you still need to know what the node was before. You got to keep track of that somewhere because that's the one whose next field you have to adjust. But yeah, you can think of it either from the back of the pair or from the front of the pair. Perfectly fine.
If there's something down the line.
No, should be fine either way. And to kickstart the whole process, right, start off with before equal to 0. Why? Because that's always the sentinel node. So start off with before equal to 0, and your initial after is going to be whatever the first node of the list is, right? Is where the sentinel node points. And if the number you're inserting is a 2, which comes before the 10, what you're going to end up doing is changing the sentinel's next node to point to your new node, and your new node to point to the 10, so that'll still work. So beginning of the list, not a special case. End of the list, that's your special case here. All right, this is pretty much your whole add routine. We did print, search is a modification on print. Delete, you have to do the same thing. You have to find your node, but it's really more like a search. And if you search before you delete, you know the node's in the list somewhere, so do your search until you find a node, and then change the previous node to point where the node you're deleting points. So you can use the same pair of pointers if you like. And that's pretty much all your functions. And you can do that without your main function, right? You can just have a main function that calls init, calls add, print, delete, print, search, print, that kind of stuff. And then once that's all done, you can work on the main program. And the main program is one big loop, right? Call init to initialize your linked list, then make an infinite loop that basically prints a prompt, calls fgets to read a string, and then just calls scanf a bunch of times. See if it parses as I%d, or a p, or an s%d, or a d%d, or an x. If it's an I%d, then go ahead and call search, and if it's not in the list, call add, and look at the return codes and print a message if necessary. If it's S followed by a %D, call search with whatever number you scanned, right? If it's not any of these things, print out your short help message. And then in any case other than X, go back to the top of the while loop and just keep repeating. If you get an X, just return, and then you're done. Yeah?
So to clarify, in the add function, we're just, we're adding stuff to the list, but like, are we?
You're good to go. I'll see you next time. Go ahead.
Actually modifying, so we're just modifying the next values when we do that, right? Not actually like modifying the actual order in which the list, that's the print function, right?
Right, yeah, we're really just modifying next.
So it was never coming down here, and we're adding the data.
We're adding a new
So we're
bunch of data to the array,
Yeah, we
right?
gotta modify it.
And we're changing the next field of the node that came before it to point to the new node. Yeah.